So in this video, we'll be graphing transformations of exponential functions. So let's actually talk a bit about the base function. Let's just recap. And hopefully by now you have done the Desmos activity, which actually addresses the AKPQ, or transformations of the exponential functions. So let's recap B. So we know that there are conditions for B, restrictions. B has to be positive and B cannot be 1. Because if B is equals to 1, well, 1 to the power of x, anything with base 1 will be 1, 1, 1. So in other words, you're going to get a straight line. And we don't consider that as an exponential function. And all right, so if B is greater than 1, all right, so based on Desmos in the previous videos, we know that this graph is going to increase. It's going to swoop up. In other words, and also when it comes to the base being positive, that means all the y values that come into, when you input any x values, all the y values that come out of it will be a positive number. So in other words, our range is going to be all in the positive zone. So we should have nothing in the, no points in the negative parts and below the x-axis. So when we graph a base what's greater than 1, it's going to have all base to the x always has a y-intercept of 1, because when you sub in x for 0 into the exponential function, you get b to the power of 0, which gives you 1. In other words, y-intercepts are always 1, and then if it increases, it's going to swoop up, curve up. And keep in mind, we talked a bit about horizontal asymptotes, the end behaviors. It gets closer, so always put an arrow to the left, indicating in this little dash, just to indicate that there is a horizontal asymptote at y is equals to 0. The other one is, well, what happens if b is less than 1? For example, b could be, or between 0, because it has to be positive, such as 0.5, 0.6, 0.7, 0.8. Well, the graph is going to swoop down. So it swoops up to the left, but then when you go to the right, it swoops down and it sort of tails off at the horizontal asymptote. So that's a recap of b to the x base graph. And in Desmos, what you should have done is, based on the AKPQ that we added on to this function here, what happens? So let's recap what the findings from the Desmos activity. So we know that b will change the way that graph goes. If b is greater than 1, the graph goes up. But here increasing. If the b is between 0 and 1, the graph is going to decrease. I'll put here decrease from left to right. Now A tells you a couple of things about the graph. It actually tells you about the range, right? If A is positive, greater than 0, the graph is going to be above the horizontal asymptote. If A is below 0, if A is a negative, we usually associate A being a reflection. It's negative, so it's going to be flipping over, flipping down. But here it's going to be below, or flip down below the horizontal asymptote. Now Q here, based on Desmos, you should have seen that it shifts everything up and down. When everything shifts up and down, the horizontal asymptote also follows. So Q actually tells you the horizontal line. All right, and over here, I believe that K, based on Desmos, it changes some features of the graph, but in terms of the significance of K is important when it's negative or positive. If K is greater than 0 versus K is less than 0, things are being reflected. I'll put here, reflected, for K is less than 0. And because if K is less than 0 and things are reflected, that means the behavior will change. Whether it increases or decreases will depends on the base function. P here, based on Desmos, it doesn't really do that much in terms of the shape of the graph, but based on past lessons, we know it just shifts things to the left or to the right, depending if it's positive or negative. So when we graph an exponential function, or I'll call it sketch, there's a couple of steps we need to go through. And the first thing is always sketch. In my book, each teacher teaches the approach differently, but I prefer that you graph the horizontal asymptote first. And the reason why is because once you graph the horizontal asymptote, you can tell right away with the A value whether the graph is above or below. And then that's why we talk about the range. And if you're not too sure about the range, because you kind of forget, maybe some students will forget the A value, the purpose of it, then you can calculate the y-intercept. Well, what's the y-intercept? Well, y-intercept means when the x is equal to 0. So you might need a calculator to do this step to determine whether the graph is above or below. And then we can calculate the y value. The next thing is the last step. There's only 3 steps. It's the shape. There's only a couple of shapes that the graph can go. Either it can go flat and go up, it can go down and flat, and becomes flat. Or it can be flipped, meaning it can look something like this. So things are flipped. So imagine me taking this and flipping it over. So it'd be something like flat and then go down. Whereas this one here, it could go down and then become flat. So there's only 4 different ways the exponential graph can look. And we'll see that in the following examples. All right, so let's look at the first example. So here, what is the b value? What's your base graph? What that means is if you remove all the a, k, p, q's, what are you left with? Well, you're left with 3. So I know that the base is a 3, and I know that 3 to the x is greater than the base is greater than 1. That means my graph, without the a, k, p, q, is going to start off flat and then swoop up. It is increasing. So at least I have a sense of what the graph looks like originally. And then this graph is going to change because we have all these numbers applying to it. And let's actually label them from left to right. A is the -2. It's a number in front of the base, which is this one here. K is the number in front of the x, which is 0.5. And here it's already factored already, so we know that the shift is going to be 3 to the right. And this is your q value. And let's just recap what each means. So the very first thing is, what are we going to graph first? We're going to graph the horizontal asymptote. So I'll put in red. This piece here tells you the horizontal asymptote. So I'm just going to draw a dotted red line indicating the horizontal asymptote, and I'm going to call it y is equals to 1 in brackets HA. All right. Now the next thing is, well, your graph, is it going to be above the red line or below the red line? Well, how are you going to know? Well, it's going to be the a value, because a deals with the reflection over the horizontal axis. Horizontal asymptote. In this case, it's negative. That means the graph is going to flip down. So in other words, I'll erase the top part. We know the graph is going to be somewhere down here, right over here, right over here. Now the next thing is, we need to figure out a dot, a point, and we're going to figure out the y-intercept. So on the right-hand side, I'm going to let y, to find the y-intercept, let's let x be 0. So that means I'm going to sub in using proper function notation. So there's my input. So anytime I see x over here, I'm going to replace it with a 0. So I'm going to copy down the equation, 0.5 in brackets, 0 minus 3, and then plus 1. And over here, the next thing, I'm just going to work this out. That gives me negative 1.5 plus 1. And then this is where you need your handy calculator, and that should give you 0.615. And let's actually plot this dot. 0.615 is somewhere over here. I should use blue color so everyone can see it's blue. All right, so blue over here, right over here. Okay, so the last part is, I consider the more challenging part, is what is the graph going to look like? Now, there's only a couple of ways. Either it's going to swoop up and flatten off, or it's going to start off flat and then go down. So which one is it going to be? How do we know? Well, let's go back and look at the original graph. So here we have a graph that's swooping up. I'll put it on the left-hand side. So start here, swoops up. But how many reflections do we have? Well, we have only one reflection, because the k value is positive, meaning there is no reflection over the y-axis, but we have a reflection over the x-axis. That means this original graph is going to flip down. So you're going to start off flat and then go down. So you're pretty much done you have the shape of the graph. You just have to incorporate into on the grid. So over here, I'm going to start off flat here, and then I'm going to reach to my y-intercept, and then I have to swoop back down. Put arrows there, put arrows to the end to the right, and you're done. Okay, the next one here. So what is the base? Well, the base is 0.7. So because the base is 0.7 and 0.7 less than 1, that means we know our graph is going to go and decrease. It's going to swoop down and become flat. At least we know the original shape of the graph. So let's figure out the AKPQ. Well, what's the A? What's the number in front of the 0.7? There's nothing. It's a 1. Nothing has happened. What's a number in front of X? It's -2. Now, what's the P value? Now, keep in mind, if you really want to find the true shift, phase shift, you're going to have to change it to factored form. In other words, this -2 must be factored out, and you have x plus 4. That means you're moving 4 to the left. And Q, but there's no number outside here. Well, that's because it's 0. There's no number. That means it's 0. That means the horizontal asymptote, I'll use red, is going to be on the x-axis. Over here is your y is equals to 0, your HA. All right, the next thing is, well, how do we know whether the range of the graph, is it above the HA or is it below the HA? Well, the A is gonna tell you. The A is positive, it's gonna be above. It is not flipped at all. In other words, we're gonna erase this part here. It's gonna be above, somewhere up here. Now let's solve for the y-intercept. Notice that the steps don't change from the first example. So let's find the y-intercept. What's x equals to 0? So you're going to sum in x into 0 into the function. All right, 0.7, and you end up getting negative 0 minus 8. And you got to put 7 and negative 8. And if you put this in your calculator, you're going to get 0.7 to the power of negative 0.8. That's going to give you 1.33. 1.33. In other words, 1.33, I'll use blue color, which is over here. So at least we have a dot. And the dot, the y-intercept actually corresponds to our range, which is somewhere up in this area here. Okay, so next is the last step. Well, what's the shape of this graph? Well, let's look at the original shape. The original shape is right over here, right in blue over here. But do we have any reflections? Yes, we do. Now, how are we reflecting this? Well, are we flipping it down and up? No, we're not, because we're not flipping it down, but we're flipping it left to right. So in other words, here we have this way here, and if we were to flip it, imagine there was a y-axis over here, or vertical axis, and you're going to flip it across to the left. What's it going to be? Well, it's going to start off flat and then go back up. In other words, you take this brand new shape, it's going to increase instead of decrease. So you're going to go start off flat, and then you're going to reach the y-intercept and then just swoop up with the appropriate, where the arrow's at the end. So when it comes to the behavior, so I'm just going to sort of like make note of this. So notice how this graph is decreasing. If you have a single reflection, then the graph no longer decreases, it's going to increase. Now, if you did a double reflection, we're going to change this question slightly. If you did a double reflection, let's say I put a negative in front of here. Well, what's going to happen? Well, you're going to do a double reflection. So you went from decreasing, then you increased, and then you're going to have to do another reflection. If I had another reflection, it would actually decrease. So just be aware of the types of reflections and how it affects the behavior of the shape. Okay, so let's have a look at this function here. First things first, what is our base? So always write down, if you can, the base is 1.7. And keep in mind the base is greater than 1. So we know that this graph, the base graph is going to start off flat and then go up. So at least we have a sense of the original graph. Now let's figure out the AKPQ. Well, the A is the first number that you see, but miss, there's no number. Well, it's a negative, and it's a negative 1. The K here is right next to the X, which is negative 0.25. Now the P, if you notice here, there is no P. There's no bracket going on here. So in this case, it's 0, no left, right shift. And here the Q is negative 2. So we're just listing things out, AKPQ. And then we start to graph. Well, what do we graph first? Well, let's graph the horizontal asymptote, which is, I'll use green, which is this one here. This is a horizontal asymptote right over here. So negative 2, so I'm going to draw my dash, dash, dash at the negative 2. That's the very first step. Okay. I'll put here y is equals to negative 2. I'll call it HA, just to tell you it's a horizontal asymptote. Next thing is, let's use blue. Let's start graphing this. Okay, so let's actually figure out where this graph is located. Is it above the horizontal asymptote, or is it below the horizontal asymptote? How can you tell without doing any calculations? Well, we're going to look at the A value. The A is actually negative. That means the graph is being flipped down. So in other words, it's going to be below, right over in this area here. Okay. So now that we know it's below, let's figure out where the graph crosses the y-intercept. Is it over here, over here, over here? And this is where a calculation is required. So to calculate the y-intercept, I'll put over here, we're going to let x equals to 0. In other words, f of 0 using proper function notation is negative bracket 1.7, negative 0.25 times 0 minus 2. And we don't need a calculator for this. Keep in mind, if you multiply this by 0, this whole thing becomes 0. And if you recall, remember, anything to the power of 0 is going to be 1. So we have negative bracket 1, and we end up getting negative 3. In other words, 3 is over here. So we have a dot. At least we have a point of reference. And we know that this dot is below the green line, so we know we're on the right track. And the last thing, the shape. The shape matters. So let's have a look. I'll use red, our original graph. So this is our original graph, the base graph, without any transformations, without any reflections. So how do I know? Because the base is greater than 1. I know the base graph is going to swoop up. But what has happened to this graph? It has gone through how many reflections? 1 and 2. So that means it's double reflected. Now, if you take this and double reflect it, well, first things first, I'll put over here to the left. If I reflected it once, over the x-axis, what happens? It's going to flip down. That's great. But then what happens if I flip it across the vertical axis? What's going to happen to this if I take this and flip it across to the right or to the left? What's going to happen? Well, it's going to look like this. Because imagine me having a vertical line and you're sort of flipping it over something. It's going to look like this. It's going to increase instead. So in other words, this graph is going to increase. When it increases, you start off low, and then you have to pass the y-intercept, and you just keep on going higher and higher. But keep in mind, do not go above that green line. And here, with the left, put an arrow indicating that's going to swoop down, and you are done. So if you look at this graph here from left to right, it's still increasing. So it's increasing. But miss, this is also increasing. The reason why it's increasing is because you double reflect. Once you double reflect, you kind of offset you maintain the increasing feature.